Multiple slits. Another name for multiple slit is grating. So if you look at this diagram, some of you might find it familiar because it's similar to the double slit setup. In fact, single slits also the same. The only difference is the type of slits that you are using here, or the number of slits that you are using here. We always have a source, the slit, and then the screen. Okay, so this is very similar to young double slits, whereby we also have the central bright fringe. Then we have the first order bright fringe, which is called a maximum, or the second order maximum. Then right in the middle we have the dark fringe. The only difference is the sharpness of the fringe, of the fringes that you see here. So if I were to take a look at the double slit, okay, in the double slits you can see that the images, right, the spots, the bright fringe that you see here is not so sharp compared to multiple slits, because in multiple slits you have many waves interfering, so the position where you have bright fringe is very precise. Any other positions there is complete cancellation. Okay, so the same equations that we use in double slit can also be applied here, but what we will be more interested is the angle theta. Okay, the angle theta is defined as the angle between the straight through position and the order of the spot that you are interested in. Okay, so for example, I call this theta 1, it will be angle between the central bright fringe and the first order maximum. Okay, if it's the angle between the central bright fringe and the second order maximum, then that will be theta 2, and so far so on. This is the derivation that I used in double slits. So for multiple slits, we can also make use of this result. Okay, that is sine theta equals to m lambda over 2. But of course, for double slits, there will be many of these slits. So we will have to do 2 slits at a time. So the equation will still be the same. Okay, at any one time we can only consider 2 bins coming to meet at one spot. So the equation we'll be using in the grating will also be d sine theta equals to m lambda. But we stop here. Okay, we don't go on to find the fringe separation. We don't go on to find the fringe separation. Okay, this is a picture showing you how the grating look like. Basically, it consists of many slits. Okay, then this is a beam of light. So the angle theta will be the angle between the straight through position and the beams of light. So remember, the screen is very far away, so these lights are all almost parallel. So at the same spot, let's say a bright spot that you see on the screen, okay, all this light will have the same angle theta. Then the distance between the 2 slits is still the same, is still small d. Okay, if instead of a monochromatic light, monochromatic means single wavelength, like red light, okay, then what you see on the screen will be just red. If you are using white light, this is what you will see on the screen. You will see rainbow. So right in the middle, you still see white because you have all the 7 colors meeting at the central position. So this is the 0 order maximum. Then for the first order maximum, because the wavelength of the lights are all different, okay, we call d sine theta equals to m lambda. So the wavelength will be affecting the angle theta. So for violet, it has the shortest wavelength. So the shortest wavelength will correspond to the smallest angle theta. Okay, so you see violet first. Then as you go higher, you see lights that are of longer wavelength. The last one that you see, right, will be red, which has the longest wavelength of about 750 nanometer. So the theta is the largest, because d sine theta equals to m lambda. So your sine theta will be proportional to your wavelength. So the larger the wavelength, the larger the theta. So this is all in the first order. There's more than one fringes, more than one fringe. So we don't call this first order bright fringe anymore. We call this a first order spectrum. Then you have the dark fringe, and then if you go higher up, you will see the next purple, next blue, next red. That will be the second order. And then if you go higher, if your screen is big enough, you can see the third order and the fourth order. Same thing below, okay, something identical to what we see on top. Okay, you have the first order spectrum, second order spectrum, and so far so on. Okay, when you go to higher order, there might be a possibility that the wavelength, let's say this is a third order, the wavelength of the purple light actually go into or overlap with a wavelength in a lower order, say second order. Okay, so when they overlap, right, the angle theta will be the same. Okay, so with that, we are done with the diffraction grating. Let's take a look at an example 7. Okay, I'll give you some time to try. Okay, assuming already tried. So you're given a beam of white light incident upon a diffraction grating, that means many slits, after passing through a filter that allows only wavelengths between 400 and 600 nanometer to pass through. So I have a spread of wavelength from 400 to 600 nanometer. You're told that the angle between the red and the blue ends of the second order spectrum, second order, so n equals to 2, is 16 degrees. How many lines per meter are there in the grating? Okay, what do you mean by how many lines are there in a grating? Because every 2 lines will form 1 slit. So if you have 3 lines, you form 2 slits. You have 1000 lines, you form 999 slits. So when the number of slits increases, we can say that the number of slits is approximately equals to the number of lines. So if you have the number of lines, okay, if you have the number of lines per meter, you take the reciprocal of it, it actually gives you the d, which is the distance between the 2 slits. Say I have, for example, say I have a length of 1 meter and there are 1000 slits. So if I take 1000 divided by 1 meter, that will give me the slit separation. So the reciprocal of that, it will give me the number of lines per meter. So this is what is given, or this is what are given. N equals to 2, wavelengths for blue, wavelength for red, as well as the angle between the second order red and second order blue is 16 degrees. For the angle here, we convert it to a radian because we'll be using small angle approximation. The only equations that we have for diffraction grating is d sine theta equals to m lambda. For blue light, we have d sine theta 2b to be equals to 2 times the wavelength of the blue light over d, where d is unknown. Okay, we need to find d in order to find out the number of lines. Do the same thing for the red light, d sine theta 2r. Okay, then we have 2 n equals to 2 lambda over d. So with that 2 equations, we need to find d. To find d, we will somehow have to get rid of the theta. And notice that I'm given theta 2r minus theta 2b. I'm not given sine theta 2b minus sine theta 2r. So what I need to do next is to use small angle approximation, assuming that sine theta 2b is small. And therefore, sine theta 2b will be approximately equals to theta 2b. Okay, so I have sine theta 2r minus sine theta 2b, and then use small angle approximation. Instead of sine theta 2r, I have theta 2r minus theta 2b, which is given at 16 degrees. Change that to radian and calculate your d. So the distance between 2 slits, right, is about 1.43 times 10 to the power minus 6 meters. The number of lines will be the reciprocal of d, which is approximately 7 times 10 to the power 5 lines per meter. Okay, so if you take 1 meter divided by the number of lines, again you go back, you get your small d, which is the distance between 2 slits. Okay, with that, let's take a look at work example 8, which is a continuation from our work example 7. So you're told that in the previous example, you're asked to find which wavelength in the 4th order spectrum will overlap with the green color light of wavelength 550 nanometer in the 3rd order spectrum. So like what I said just now, as you go higher, the wavelength, the longer wavelength in the lower order spectrum might overlap with the lower wavelength in the higher spectrum. Okay, so in order for the two wavelengths to overlap, we need them to be at the same position. That means the theta must be the same. So theta 4, the light in the fourth order, must be equals to theta 3, the green light in the third order. Then recall we have sine theta equals to n lambda over d. So sine theta 4 will be 4 lambda over d. And sine theta 3 will be 3 lambda over d. So with that, the only unknown here is actually your wavelength lambda. We don't even need to know what is the d because it cancels out on both sides. Okay, with that we get the wavelength 413, and that's the end for the lecture. Thank you.